Welcome back from the break. We're moving into our next speaker now. It's a user presentation from Infineon, from Holger Busch, who I've known for a long time when I used to work in formal verification at Infineon. Holger is a senior staff engineer at Infineon Technologies based in Germany. The title of his talk is Verifying Safety Specifications Compliance of RTL Designs. Holger Busch is currently a verification and digital design engineer in the automotive division of Infineon Technologies AG, with a special focus on formal functional verification and the design of safety hardware of microcontroller product families, and automated methodologies and flows for design and verification according to ISO 26262. And for those who don't know ISO 26262, it's the automotive standard for safety. So we're going to hand over to Holger. Holger?
Yeah, I'm here. Good morning, everybody, or good afternoon, depending on where you're located. Yeah, thanks for the introduction. So I'm covering several aspects of the safety verification work, which is also funded in the funding project EMC Square, which Mike Bartley is also taking part in. And so I hope that it's now everything works. Yeah. So this is the agenda. I first talk about safety mechanism for registers, and then, since the talk is related to specification, I talk about this topic, and then how to verify this, and then the main part of this is how to achieve the safety specification compliance. So probably most of you already know the automotive safety standard ISO 26262, which addresses automotive designs and everything which is related to the development of road vehicles below 3.5 tons. And this, of course, since we are SOC supplier, we also have to comply with this standard, and specifically we need to provide diagnostic coverage according to automotive safety integrity levels A to D in order to be ready for safety applications like braking system or automatic driver assistance systems. We also have to address the availability of mission function. Therefore, our microcontroller designs must provide in very critical areas also not just error detection but also robustness. And we must equip our safety mechanisms with self-testing facilities. And since safety is always some kind of a moving target, we need to provide some flexibility to be able to satisfy varying safety requirements, which may be different for different customers and different target markets. But since we are developing product families, we must be prepared to have some flexibility to configure our products in different ways, so that the final derivatives really address the needs of the specific customers. And there are always conflicts between product and safety requirements, because safety means additional power and area, and therefore we need to be able to balance this. Of course, like everyone, we want to minimize the efforts and the costs which are related to these extra safety measures, because this is definitely not only for the design itself, but also for the design methodology. It has a huge impact, and therefore we need structured methodologies to be able to manage this extra effort. Here are some excerpts from the ISO 262 standards, some definitions. So the standard explicitly mentions that registers, that safety measures should be implemented for registers which are different roles in processing units. They are used as general purpose registers or for control. And you can well imagine that if an important control register has some spontaneous fault, then this can have a very bad effect. And also configuration register, if you think of clock control registers where clock dividers would be flipped by some alpha particle, then you would have completely wrong clock frequency configured, and this would be very bad. Therefore, we need to take some measures, some safety measures or safety mechanisms. We need to install them either in software or in hardware, and they should also be equipped with some self-testing. This is explicitly mentioned by the standard, so that we can, from time to time, check whether the safety mechanism is still alive and still operating. And safety mechanisms are normally used based on redundancy and parity, EDC or ECC. So some different approaches to achieve error detection and correction capabilities. The latency is also defined in the standards, so there shouldn't be. So the goal is whenever some spontaneous fault occurs, that the system is driven to a safe state before a hazard can occur. Everything is statistics, of course, but if we, as a chip provider, can guarantee that our alarm mechanism is sufficiently fast, then we can meet the requirements of the standard. So in this example, we assume that some fault occurs in some module of a complete system or chip, and then this fault is propagated to the boundaries of the module, and then to a safety management unit, where some reaction has been configured, and this is then spread to the rest of the system or chip in order to drive the system into a safe state. We have for safety registers, we have a hardware safety mechanism, which is just summarized under the topic SFF, safety flip-flops, where we project registers of any widths, because there are many different widths occurring in a design and different modules. This is based on redundancy and provides detection, but also optional correction where it is necessary of transient soft errors. And it provides 100% diagnostic coverage and a very short diagnostic test interval until an alarm is occurred and propagated to the safety management unit. It reports actually all failure modes of the safety register paths and of the monitoring architecture, like clock monitors, to the safety management unit as alarm triggers, where then the configured alarm reaction is started. This mechanism is testable at any time during the driving cycle and has no interference with the mission mode. So it can be run several times. Whenever some problem has been found, then software can decide to start this self-testing somewhere. This user, of course, since redundancy means area overhead, it has to be carefully specified by safety concept. This is based on separate analysis like FMEA, so failure mode effect analysis, and also with FMEDA with diagnostic coverage analysis, fault tree analysis, dependent failure analysis, which contains a common cause failure analysis. So the safety concept allocates the safety measures. So there are many different, of course. I'm just talking here about safety register mechanisms, SFF. So they have to be allocated to the microcontroller parts at a very high level first in the safety concept, depending on the functional safety requirements, which already suggest concrete safety measures for different components of the safety architecture. But of course, they need to be then refined, and since the architecture is then described at a lower level, or the components of the architecture, then the technical safety requirements, actually the different safety mechanisms are refined and allocated to the subparts of the architecture. This is based then finally on the safety analysis and the RTL design, because some safety critical function is not directly visible or cannot be related in the global safety concept, which is actually concept and doesn't contain all the details of the design, but in the design itself it also needs to be analyzed where safety measures needs to be taken. For instance, for internal registers which are not visible at the concept level, but we contribute to safety critical function. So here's an example of a simple duplication of a normal flip-flop, which is used in the design in this SFF safety mechanism. So here an inverted version of the information stored in the productive flip-flop bit is then stored in an additional bit, and an alarm is raised whenever there's any discrepancy found between both bits. This is just able to provide detection whenever a bit is flipped spontaneously. If we have triplication, then we are able to do also correction by majority decision. We call this here SFF2. So this is just a very simple approach, but we can also use ECC protection, where we have more advanced ways of we need encoding logic before, and in order to generate an additional ECC error-corrected code, and this is stored in a register, and then the decoder, whenever the register is read, the information is decoded, and the actual the read ECC is compared with a newly generated one, and then if there's any discrepancy between this and an error, depending on the capabilities of the ECC approach, 1-bit errors can be corrected and 2-bit errors detected, but there can also be higher orders of errors be corrected depending on the number of redundancy bits. So the difference to the simple approach is that we have a distinction between correctable and uncorrectable errors. We have less redundant flip-flops, but of course we have some overhead for the encoding and decoding logic, which typically contains a lot of XOR gates. So, and therefore it depends on the application and on the safety requirements whether actually this simple version is with duplication triplication is used, or whether parity check also is a different approach, or ECC based safeguarding is installed. So the question is now, how do we specify safety critical functionality, and especially for registers? We normally have register specifications which have global items for the complete register, like the access modes, but then some special access protections are installed, which allow only in very few, if the access is enabled, to modify the register. Typically for configuration registers, this approach is used, but there are also bit field-wise specifications needed. First of all, the register bit field layout has to be specified, and then also there might be some offset address being specified if some registers or parts are used in different modules with different base addresses. Then we need to specify offset addresses. For these, we have reset values, which can also be individual for different bit fields, or reset classes can be individual, can be either global, normally it's global. For a complete register, it can be a system reset or a power on reset or an application reset, depending on the usage of the register. Then we have different access modes, access types, like read-writable, only by software read-writable bit fields, or ones which also are modifiable by hardware. Some ones are only modified by hardware, typically status registers, and some bit fields are just used for clearing other bit fields. This is different. So there are many different bit field types available, and they are specified in this register specification. This is typically an XML format, which is given here in terms of tags, and this can be processed by other tools and can be, for instance, used for formal verification or for SOC verification. So there are different usages of this information, but it's a formal information which is important, and so we can also generate formal property code from this. And we have additional tags which not just related to software, to what is visible outside from the perspective of the bus, but also inside the module, where there may be some specific conditions, like hardware write conditions, which cannot influenced by software, but need internal conditions. They are also specified in such an XML format and can be merged with the so-called black box specification text. And now if we take a look at how these are related, so we can generate also VHDL code from this. In principle, we do this in very few areas so far because we use a lot of existing and modify existing modules. But in new modules, we can also generate VHDL code for registers. But since this information is formal, we generate automatically formal verification property code from this information. And here are some aspects related to software writing and reading. So what is visible externally from the bus is specified in these tags and translated into formal verification code. And then we have these internal conditions like hardware write and conditions and hardware write values, which are then the second category of white box tags, which are also specified and translated into formal property code. And from this, we generate automatically formal properties and checks, and which cover the full functionality of all the registers. And how do we now combine this with the safety function? Well, there's a superposition principle, since we can exchange the safety flip-flops with normal flip-flops. So we can, if we know that some register is safety critical, we keep the normal function information as it is and just add some safety information, which then controls whether a safety flip-flop is used or not, together with some alarm functionality, of course. So this is typically done when we have for each register, this is done in such a way that the bit fields are analyzed and categorized. There are safe bit fields which do not influence any safety function. There are bit fields where detection of bit flips is sufficient. There are other where even correction might be required. And this can be specified also in this XML format by concept engineering and has to be implemented by the design engineers. They are just simply merged with the functional tags. And since we are talking about product families, so we can have different XML files for different derivatives of a product and also with different safety requirements. So this means that we have done the allocation when bit fields are classified as normal flip-flops. They are safe, and if the detection is sufficient, then these bit fields get this assignment to be implemented as safety flip-flops or safety flip-flops 2 if there's correction required. Of course, this is very well suited for formal verification. Since there's a regular structure, there's a formal description of this specification, therefore it's well suited for formal verification. And if we have a safety mechanism, we want to achieve ASIL-D, which requires 99% of all single-point faults to be detected, and we want to also to check that the diagnostic test interval does not exceed the limit that's what's required by the standard. And this is reflected by properties which check that any error causes an alarm with a very small latency time. We see some examples on later slides. We check that there's no false alarm being raised, which is also very important. We check that any correctable error, which should be correctable according to the specification, is in fact corrected. That's how if we consider self-testing, we also want to make sure that the self-test interval raises the alarm as if an actual fault had occurred, and therefore specific properties also take care of this and check the fault reaction time of this. So we have exhausted formal verification with fault injection for all this to verify this. For self-testing, we actually don't need directly fault injection because this self-testing itself does some internal hardware fault injection by flipping bits, but even this can interact with real faults. So we also run self-testing checks together with fault injection tests, but also without. If self-testing is not active, then we also do checks with fault injection. And we see on later slides how this is done in formal. So we use for this automatic functions to generate properties based on signal extraction, because in the insensate design all signals are available and can be used in formal properties. And since we have some predefined properties, as we see in a minute, we can then extract filtered signals from the design and feed them into macros, which are then used on the formal generic properties. The proofs are then run automatically. For fault injection, we use, by the way, we use a formal property checker for once. The previous talk was about this property checker already. So it has a very nice feature for formal fault injection. It allows you to cut any signal into a fan-in and a fan-out part. And the fan-in part gets an external input of the complete design, and the fan-out part gets an external input. And then you can make any fault assumption on these two parts of the signal. So if we connect it, we make an assumption. This input is identical to the output, then we have no fault assumption, and then we can assume a stuck fault 0, an inversion, or a bridging fault. If we have a safety flip-flop or some if we were to verify some bridging between, that's the effect of some bridging, that it is detected between any two signals, we can easily specify this by just relating the two cut signals and the inputs and output parts of this in one assumption, a very simple assumption. And if we model bit errors at a more global level, it turned out that it is very convenient to combine the signals which are to be checked and fault injected into vectors, and then have a vector for the input fan-in part and also for the fan-out part. We have now, just talking about the safety flip-flop mechanism with duplication, well, then we have a second part for the other flip-flop, and then we can relate this in a fault vector, and each position of this fault vector, which is generated by the XOR at vector level function, and if we count then the ones of this difference error, of this difference vector, we have the number of faults which we assume, and then we can write properties which say that we detect any single bit fault, for instance, and express this quite conveniently with such a macro definition. And all these macros are generated automatically from the design, because we just filter the signals by some heuristics and get them from the instance names of the safety flip-flops, for instance, and can relate them directly based on the structural information from the design. And in principle, then we have a couple of such simple properties. If there's a fault, then there should be, so it's just an implication, there should be an alarm and also a test alarm. Test alarm means that in order to distinguish between whether the alarm has been generated by some self-testing fault or some expected fault or some unexpected fault, where the test alarm is generated. So we can then prove. So I guess it got the information that I'm muted. That's right. In this property, we assume that up to a certain time point t1, no error has occurred so far. But then at time point t, there's a 1-bit error, and there should be now an alarm being raised, and also a test alarm, because this is an unexpected. It has been generated by some fault injection assumption that somewhere in this long vector, just 1 bit has been flipped. And this is bound to generate an alarm, as expected. And this property is proven quite efficiently. I'll give later some results on this. So this is the aspect that we can very efficiently, by fault injection, run properties. And we have safety modifications, which are also must ensure that whenever we install a safety mechanism, there should be the function, the actual mission function should not be affected at all. So we have to do some equivalence checking. We do this very local, because whenever the subcomponent is modified, we take just this subcomponent and generate properties automatically from the outputs of. We take the original design and the the safety-equipped design and compare just the outputs and make some assumptions about this. First, we make an inductive proof that for all of these outputs, the equivalence is given. There's kind of some inductive equivalence check. And we can make the same with fault injection. And then if we just inject correctable faults, we must be able to show, of course, first that the alarms are generated, but also that still the outputs are the same, because the faults have been corrected, and therefore the outer function should not be affected at all if these are just correctable errors. So how we verify now safety specification compliance? Because if we just verify that the safety mechanism as such works on all registers which have been protected, and that the installation does not corrupt the regular function, this is very good to have this already, but it's still not assured that all specified safety critical registers are actually covered by the safety flip-flop safety mechanism, because otherwise there could be some forgotten registers where this mechanism was supposed to be installed but wasn't actually, or there can also be some superfluous safeguarding installed, which means a waste of area and power, so both should be avoided. And therefore we make quite a simple approach, but which is based on fan-in analysis, where we follow from the functional register value, which is just provided to the rest of the circuit, just the normal functional value, and from this this is expressed in terms of a signal, of course, in the design, and this is followed by fan analysis down to flip-flop. And if this finally turns out to be a safety flip-flop signal, then it's clear that it's protected. If it's just an ordinary flip-flop, then it's not protected as expected. And that's we can compare this with the original specification in this XML format, and by this we get a full coverage of the specification, and that we know that the design has actually been implemented in the specified way. So there's an automated procedure for this. The fan analysis of the signals depend on the functional register values, and we can do automatically the fan analysis, and we get the information that all registers which are safeguarded in the design are really safeguarded as specified, and also the other way around, that all FF specified registers must not be safeguarded, can also be conferred by formal verification by the generated properties. Crucial for this is that we have since OneSpin has a lot of useful tickle functions which are open to users, we can easily implement such, I would say, apps, which they are very application dependent apps based on what we have in our specific designs, and can write them and configure them in a way we need. Then I come to the end of my talk. So there are a lot of this automatic macro generation is very efficient. It just costs seconds, because it's even if there are several thousands of lines property code being generated, this is very, very fast. And we have just a small set of reusable generic properties which are sufficient, and they are instrumented with the generated macros. We've found all potential faults which are covered by just few properties, because we always say there's just one single bit error in the complete vector, but we don't say in which position, and therefore all the positions are covered by this property. So this is very efficient, and we can, for instance, have 3,000 arbitrarily combined faults verified in 25 minutes. It's slightly more expensive, so maybe 1 hour to prove that there's no false alarm, depending on how the structure of the design is organized. And we have found some typical faults, like that not all SFF bits are included in alarm reduction, and some SFFs have been not correctly integrated, that also some superfluous bits were protected in some designs. So this is very efficient. We have exhaustive formal safety verification of the safety measure function, including the fault injection, and we have achieved the proof that this safety mechanism, all registers which are safeguarded by this have 100% diagnostic coverage. And then we have done sequential equivalence checks by generated properties, which are quite local and therefore very efficient. And we have the full debugging support of a formal property checker for this purpose, so it's very convenient also to use. We have generated properties for verifying safety specification compliance based on the fan-in analysis, and we have in total achieved very high proof automation by these predefined properties in combination with design-specific generated macros. And there I'm at the end of my talk, and I think hopefully fulfilled my time limits, and therefore you can ask questions now. Hello?
So we're going to move to questions. Are there any questions from Reading? So, there's a couple of questions from online, Holger. We still have quite a lot of people online. The first one is, so are these proofs built into the tool, or are they been written by, these properties been written by Infineon?
They have been written by Infineon.
Okay.
Yeah, because they're related to our hardware and to the way we install the safety mechanism. So they were specific for our designs. And of course, we also made our designs verification friendly. So this mechanism has been designed in such a way that it's very well formally verifiable.
Okay.
And therefore, it's a dedicated proof automation procedure for this mechanism.
Okay, but this work is publicly available through the EMC2 Europe project, correct?
Yeah, I mean, at a non-confidential level, of course, a part of this can be made available at EMC Square, yes. Actually,
okay,
I gave it to this project meeting, and at that level, I can provide information. Also, I published the Becon conference.
Okay, thanks, Holger. One more question online.
Mm-hmm.
The second question online is sequential equivalence checking, or sequential proof, is usually very difficult to do with the tools. So is the type of design you can do very limited with this technique?
I mean, it's efficient in this case because I have two very similar designs where just, for instance, if it's a safety mechanism has been installed and the mission function should not be modified, this is guaranteed by the way we install the safety mechanism, then we know that it should be identical, and there we can also use it at subcomponent level, so we don't have to throw the complete SOC to this equivalence checking, but only subcomponents first. And therefore, it's quite efficient also due to this inductive approach, which is, again, tailored very much to the safety mechanism. The normal combinatorial equivalence checking approach would not be applicable in total because we have different registers in. Depending on whether you have triplication or ECC protection or something, the structure, the flip-flop structure, the register structure is not the same. Therefore, it would not be possible to apply directly combinatorial equivalence checking.
Okay.
I think one could use normal conventional equivalence checkers on this problem if they have a sequential equivalence checking capability. But I found it convenient to have local properties and local checks which are very fast. And also, if it comes to analyzing the counterexamples, having the debugging infrastructure from a property check also helps very much of finding the root causes very fast.
Okay, Holger, I don't think there's any more questions from Reading. Oh, there is one. One's popped up. Oh, sorry. I think it's more marketing than question, but I'll let it go.
Hi, this is Christian Busch from again. I don't know who asked that last question, so just as an info thing. So, well, Holger came up with some fantastic system, custom-made, tailor-made for their application. At OneSpin, we have a project also where we're working on a general purpose solution. So whoever asked that question, if that's,
Okay.
Thank you.
Okay. I think you may also be able to deduce from that that Infineon are using one spin to do these proofs. So, okay, thank you, Holger. Thank you.